Morning.
Morning.
Happy to see most of you. Some of you are back. Some. Everybody, no worse for the wear after a week of spring break. Not a really enthusiastic or anything this morning. Okay. I can see what's maybe a day where we have to do some squats. I can see that. You may be there. It's okay. All right. So, I'll give you guys a test on Wednesday. For one thing, I still haven't gotten the ones from the testing center, which is awesome. But then I want us to go ahead and try to get through today's lecture and things and not take the amount of time to take to do all that. So we'll get tests on Wednesday. Generally pretty happy with how the test went. You guys did a good job on short answer. I think y'all were better prepared for that than last time. A few of the multiple choice ones, we missed some points there, but generally, I think you guys are gonna be pretty happy with how those things go. Okay. So several people have already asked. Yes, we will probably push back the third test by another week or so. That's kind of where we're running. Seems to be there. I will try to map out those things after, assuming we get through today and Wednesday, kind of map that out for kind of where we're going. Okay. So I know some folks had asked, folks were going to be gone, have some things planned and all of that. So we'll try to get a good handle on that by Wednesday afternoon, so you guys can kind of make plans. Okay. All right. Other questions or comments? Anybody doing anything particularly great or particularly terrible that you just want to share with the group? No. Okay. Well, that's where we are, then that's where we are. All right, so we're gonna start today by talking about some things that have to do with you have metabolism running, okay? And as you guys did a nice job of remembering, all of the pathways are on all the time. But one of the things we're going to highlight today is you cannot measure anaerobic metabolism. Okay. So glance at your neighbor or someone around you and try to guess how much creatine phosphate you're using at that moment. You can't really do it. Okay. How much glycolysis are they doing? You can't really do it. We can try to measure lactate in the blood, but that by the time it gets into the blood, that's not quite as accurate as we would like either. Okay. So we're going to talk a lot today and probably some on Wednesday about measuring metabolism and the metabolic response during certain kinds of exercise. What we're really going to focus on is aerobic metabolism. Okay. Because that's the one that we can measure much easier. Okay. All right. So if I want to know how much energy you guys use at a given time, I can try to quantify that in several different ways. We'll talk our way through a few of these. You guys should have seen most of these things in Principles of Health and Fitness and talked about this. Okay. But the best way to know how much energy you are using while you're sitting there right now is something called direct calorimetry. Okay, direct calorimetry. Direct calorimetry measures heat. Okay, measures heat. The thing that we haven't really discussed about metabolic equations are that one of the sort of largest byproducts, if you want to call it a byproduct, of aerobic metabolism is heat. That's why when you're cold, you shiver. Start involuntary moving, it raises your metabolic rate, you produce more heat. In theory, it warms you up. Okay? It's why if you don't sweat, as you guys will see later when we exercise when it's hot outside, we will cook ourselves in essence. Okay, because we make about 60% of our energy gets converted to heat. So how do we do that? Well, it's not just like everybody stand up and do jumping jacks and then like touch your neighbor, put your hand in your neighbor, you can feel the heat coming off of them. You probably can, but that's not enough. It's not just a put a thermometer in your mouth or in your ear or something to measure it that way. We have to put you in a big chamber. It's called a direct calorimetry chamber or a calorimeter, okay? It's insulated, it's airtight. It has these tubes or pipes in the wall, and we run water through it. And we put you in there, and your body gives off heat, and it raises the heat of the water ever so slightly. And we know how much energy has to be given off to be able to, I'm gonna move on to the next picture here, I think, maybe. We know how much energy or how much heat has to be given off to raise 1 gram of water or 1 milliliter of water 1 degree Celsius. And so for every little bit that it goes up, we can calculate how much heat you're giving off. And if we know that that's 60% of your aerobic metabolic sort of energy production, then we can calculate those things. So it looks sort of like this, okay? You have it's usually a room, a relatively small room, and you can put furniture in there. Lots of them are set up to look like a 1-bedroom apartment or a studio apartment. It has a couch and a bed, and you just go and you live in this room for a week, okay? You can put a treadmill in there, you can put a Peloton bike, you can put weights, like whatever you want, and then you can exercise in there as well. This is less, I mean, it will measure what happens during exercise, but it's kind of better for these longer, kind of slower changes and things that we're going to be able to see. Okay. Direct calorimetry is amazingly accurate. It's very, very, very accurate. But it's wildly, like so many things, it's wildly kind of unapplicable to most of our daily lives. As far as I'm aware, there is not a direct calorimetry chamber in the entire state of Oklahoma. Nobody has one. Okay. I know they have one at the medical school in Little Rock, Arkansas. I think they have one at the Children's Hospital in Kansas City. I'm sure someplace in Dallas, there's going to be at one of either the hospitals or one of the universities, there's one. But they're not that common. They have one in Germany. It's in Germany. It's in Switzerland. But it's an exact replica of the International Space Station. And obviously you can't simulate a space flight, but what they will do is they will take potential astronauts and put them in there. And like, you're going to live in here for a month, right? And so one, it kind of trains them to, this is your space, this is what it's like, and those kinds of things. They also have one that will do it that way. So a very, very accurate way. But what I want us to understand, what I really want you to take away from this is heat, okay? Ways that we quantify aerobic metabolism. The best way is heat, okay? Best way is heat. Okay. Another way to assess, though, is much, much more common. Many of you have probably already done this. I know some of you are doing this as part of your capstone project, and it's called indirect calorimetry. Okay? Somebody tell me, what does indirect mean?
Like not direct contact at all?
Not direct contact, okay? But anything else? If you took an indirect route to get to class this morning, what did you do? Jason, like, did you take the the easiest, the straightest kind of way, and you went around? Okay. Indirect calorimetry. We are going to not measure heat production. We're not measuring something in that way that was a direct kind of thing. We're going to measure CO2 production. And we're going to estimate O2 use and therefore calorie use or energy expenditure based upon CO2 production. Okay. And so if we know in the air that there is a certain amount of CO2, there's a certain amount of oxygen. If we collect the air that you breathe out, we can look at the difference in oxygen and CO2 in the air that you expire. And then based upon that, we can back calculate roughly how much energy you are using in aerobic metabolism because, right, we make CO2 in the transition step into acetyl-CoA and then throughout the Krebs cycle. So again, things that we're doing in metabolism, we're not measuring directly ATP, but we're measuring something that is going to be sort of in that process of how we do all of that. Okay, that gets us two terms that you guys have heard before, but I want to reiterate these because they're really, really important. The first is something called VO2, or oxygen uptake or oxygen use. The V stands for volume. So it's the volume of oxygen that is being used, or sometimes the word is consumed, okay? This is the amount of oxygen that we think we are using at the end of the electron transport chain, okay? The end of the electron transport chain. X amount of oxygen in the air. If we then look at the difference in oxygen from what's in the air to the air that you breathe out, that will give us some estimate then of anything that disappears was going into our tissues and theoretically being used. Okay? VCO2, or the volume of carbon dioxide produced, okay, is the amount of CO2 that we are breathing out. It's in expired air. Okay? Now, there's going to be a ratio between these two things. We'll talk about it in a few minutes. But for all of the sort of oxygen that we use at the end of the electron transport chain, there should be some, as O2 is used out of the air, CO2 should be produced. Okay? And the amount that that is going to vary based upon if we're using carbohydrate or if we're using fat as our energy substrate in aerobic metabolism. I'll walk through that in the next few slides. Okay? So from these two things, we can get an idea of what we're going to call indirect calorimetry, which can be quite accurate. Okay? Here's a lovely 1980s, I hope, picture of a person running on a treadmill. We're collecting the gases that they are expiring, okay, and running it through something called a metabolic cart. It's just a thing that has sensors that measure CO2 and oxygen. Okay, so breathe out air, look at the changes that are going on there versus this known room air that we're going to have, and we can then try to estimate what is happening. The good part about this is it can detect changes that happen quickly. Okay, you guys start moving right now. I just tell you, think about moving. Breathing begins to go up without even having done anything. Okay, you're preparing for this. Your heart rate goes up, and so it can track changes that are going to happen really, really quickly. So we'll see some graphs. We'll talk about this a little bit later on. Okay, I'll talk about one other thing here before we go on. How many of you could look at something right now and guesstimate how many calories you've burned already today, how much energy you've used to this point today at 8:17? Show of hands. None of y'all can? Okay. Nicholas, you can?
I mean, I can guess.
You can guess. Some of you should be able to do things without having to guess. So look around. Bring, what are you doing? What are you looking at?
What time it is?
What time? Anything else on that watch that you might be able to tell us?
Yes.
Okay. How many of you have an Apple Watch? Every one of you can look at your watch right now or your phone and get an estimate of how many calories you've burned up to this point in the day, right? If you have a Fitbit or an Oura Ring or a Whoop or whatever one of those things are, right?
Whoa, what's that?
A Whoop. Don't have to guess what a Whoop is?
Never
It's
get
just a wearable thing. It's a wearable device, and it will measure like GPS and heart rate and heart rate variability and all of those things.
Surprisingly, out of all the watches I've heard, I've never heard of that one.
Okay, it's very popular. Apparently, maybe it's less popular than I thought. How is your Apple Watch determining your calorie? Heart rate. Okay, heart rate. We haven't talked about heart rate, have we? Okay, so one of the things that happens as energy expenditure goes up, as VO2 goes up, or the CO2 goes up, is the corresponding thing that happens is cardiovascular system initiates changes. So heart rate will increase to increase cardiac output to bring more oxygen, or put more oxygen through the system. And that's how your watches are doing this. So heart rate is sort of like a double indirect, right? It's not even measuring anything that has anything to do with metabolism. It's a thing that responds to changes in metabolism. And actually turns out to be quite accurate in a lot of different ways. But that's one way that we can do that. Okay. Okay. Now, from your watches, the Apple Watch doesn't do it very well. Anybody else have one or some kind of a device that will tell us your resting metabolic rate? Resting metabolic rate. It will tell you like your energy use while you're sleeping. Let's just say. No? Okay. So resting metabolic rate, all of you are sitting there. We're not great this morning, guys. I'm not gonna lie. We're not real energetic this morning. We're not kind of back. I know y'all have like 6 weeks of being a college student, many of you left, right? I know that we may be really on that downslide of things, okay? Or like, oh God, maybe it's like 5 or something, okay? I know we're really on the back end of things, okay? But kind of point, y'all are very kind of low energy this morning. You're very close to your resting metabolic rate. You have, if you just lay in bed and do nothing, your body uses a certain amount of energy to stay alive. Okay? That is basically resting metabolic rate. You're awake, but you're there. Okay? Usually it's measured as whole body oxygen consumption. We have you come in, you want to do this, Dr. Pinku's lab is doing some stuff. You come in, you lay down, we turn the lights off, we put this little kind of bubble hood over your head. And it's hooked up to the metabolic cart. You turn the lights off, you just lay there and take a nap for half an hour. Okay, it's pretty spectacular. Okay, that tells us resting metabolic rate. Basal metabolic rate is slightly lower than resting rate. Basal metabolic rate would essentially be what you would use if you were in a coma. Okay, this is the bare minimum that has to happen to keep you alive. Okay, keep you alive. So I put these two things on here because there's some interesting stuff that goes into this, okay? If you look things up, it will say that resting metabolic rates, right, are going to be very, very dependent upon muscle mass. The more muscle you have, it is metabolically more costly just to sit there with muscle than with any other kind of tissue, okay? Because even though the muscle's not doing a whole lot, it uses more energy than, say, fat. Fat uses 0 energy to sit there, okay? Other kinds of tissue use 0 energy. Muscle, the nervous system, they're going to use some. Minimum energy requirements, people will say that it varies between 1,200 and 2,400-ish kcals per day. That's too high, okay? Most of you have a basal rate. Ladies, most of y'all and some of our smaller gentlemen, probably 800. Okay, 700-800 kcals. Right? If you have a little more muscle, weigh a little bit more, we're taller, right? Which can also help us weigh a little bit more. Maybe we're going to get into the 12, 15, 1,800 kcals per day in that instance. Okay. Most things, if you look at, will say your daily energy use is between 1,800 and 3,000, right? You've got basal rate or resting rate, plus whatever you're getting from moving around and doing things. I think most of those estimates are way too fucking high. Okay? I think they're really high. You look at what your Apple Watch said. Anybody want to share with us? Mine was dead this morning, so I couldn't. I did not charge it last night. I would have showed you guys what I didn't do. Or, as my wife likes to point out, we spent 6 hours in the car on Saturday, and she still had 12,000 steps. That's what it's like to be a parent. And he shakes a toddler around. What did you do yesterday? You guys look and see from your Apple Watch, like how many calories you expended yesterday? No? Grace, you were just like down, nothing?
I was running,
Okay, you were running?
rotting.
Rotting, yes, okay.
I have mine.
Okay. Bernie, we gotta admit now that Bernie may be a little, how far did you run yesterday, Bernie?
Actually, luckily, yesterday was my day off.
So your day off, okay, great. Watch this will be fun.
1,906 calories burned.
Okay, so how many steps did you take yesterday?
Distance, distance total did over just a mile, then probably not that much longer, like 2,362 steps.
Okay, just over a mile. That was it, okay? There's fascinating data on people that are very highly aerobically trained and that run or bike a bunch. You know what they don't do the rest of the day? Anything, right? People that have like one big, large bout of exercise tend to sit more the rest of the day than people that don't. There's just some compensatory things, okay? I think your estimate's a little high, but that's okay. So 1,900, 1,800, somewhere in there, okay?
Well, I didn't exactly sit around all day yesterday.
Did, okay, so there we go. But that's what our watch tells us these guys. Okay, so we have this data available to us, all right? That's resting metabolic rate. That's using heart rate, that's telling us these same kinds of things, okay? So there are a few other things that we need to make sure that we understand here. We talked about that more muscle mass is better, right? Muscle lets you eat more. At nearly being 46 years of age, this is what I think about in life. Okay, more muscle means I can eat more Doritos. That's just the way that we can do it. Body surface area matters. Body temperature matters. Those are kind of related. Okay, the larger your surface area, then the better able or not able you are to dissipate heat. It costs us energy to dissipate heat. If you are in a place where, say, you have a fever, your body temperature is up, you burn more calories, okay? Or you are in a place like, just say, your air conditioner has gone out and it's hot, right? Then that's going to be a thing. Stress and hormones also play a big deal in the midst of this, okay? Stress raises metabolic rate, okay? Certain hormones raise or lower metabolic rate. Thyroid hormone plays a huge role in all of this, okay? A huge role. These statistics would tell us that someone in class is likely hypothyroid. Anybody hypothyroid and care to admit? Okay. Did you take replacement? Yeah. Okay. Did they have to play around with your dose when it first started to try to get it right? Okay. So if you're hypothyroid, don't make enough thyroid hormone. One of the hallmark signs of this is weight gain and sluggishness. Okay, people are just kind of like low energy. Just here, we give you, if I gave all of you an injection of T3 and T4, I'd make you real, just like wired up from all of that. Okay, changes your sleeping patterns, it changes your moods, does all kinds of wild, crazy things, but it has a really, really big effect on resting metabolic rate and those kinds of things, okay? So just keep those kinds of things in mind, okay? So let's talk about what happens during exercise. We've covered some resting things, okay? We've covered rest. You're just sitting there, you burn a little bit just by sitting there and not doing things. Let's talk about what happens during exercise, okay? Everybody, I want you to draw something on your paper or on your iPad or something here that we're going to not cover for a couple more slides, but I think this will be really, really helpful. Okay, I think that this will be helpful. Okay, I am standing here. Okay, standing. Draw my energy use as just a flat line. It's not zero, but it's just flat. So just on your piece of paper, just draw a little bit of a line. Okay, and write standing over it. Okay. Y'all got that? All right, good. Now, someone pick a type of aerobic exercise. It's exercise matters. Pick a type of aerobic exercise. What do y'all want me to do?
Jogging.
Jogging, great. Love it. Okay, I'm gonna start jogging. What happens? Okay, what happens? I'm here, it's flat. As soon as I start jogging, what happens to the amount of energy that I need?
So,
Goes up, okay? Goes up. Does it go up gradually? Does it go up very sharply? Like, what does that look like?
I imagine sharp.
It's correct. It is sharp. Okay, straight up. I need, let's just say, 10 calories a minute. That's probably an overestimate. I need 1 calorie a minute. Also, probably not. Anyway, something here. As soon as I start jogging, okay, the first moment that I go, my energy needs to generate that force immediately jumps up. So draw a straight line going up, okay? Straight line up. And then I'm going to keep jogging. What is happening to my energy use now? Hasn't changed from where it first went up. It's flat again, okay? So it goes up and then it's flat. Assuming that my body weight doesn't change, assuming that the ground is flat or the elevation does not change, and that my pace doesn't change, okay? So during exercise, energy use, okay, is proportional to work input. But when you transition, what I showed you guys is this transition from rest, immediately up, and then, okay, once I pick a work rate, it's going to be flat. So now I'm going to do this different. Same thing, same graph, okay? We're going to draw a second one. I'm resting again, but I'm going to transition not to a jog. Okay, it's a much faster. What's going to happen to my energy use in that one compared to the jog?
Like just walking.
Okay, it's going to rocket up. Okay, it still goes straight up, but it goes up higher. Okay, it goes up higher. Okay, and then if I keep, once it goes up, if I keep that pace, it will level off again. Okay, it will level off again. That's this idea. You all get this intuitive. Okay. Energy use during exercise is related to what we would call work rate or exercise intensity. Okay. Work rate is dependent upon what thing that muscles generate. Work is what multiplied by distance. Force multiplied by distance. Do I use energy to generate force? It all comes back to the CrossFit cycle. It always comes back to the CrossFit cycle. I'm sorry. But it does. Okay. Energy use is proportional to work rate. You all get this. I'm walking, it's flat, I feel a certain way, I use a certain amount, I start going up stairs or up a hill, and it feels more effortful, right? I breathe harder, I make more heat, whatever it's going to be, okay? That's because it's proportional to work rate, okay? And that's where we're gonna be. So, the effects of exercise on oxygen uptake. Most of what you guys are gonna see, most of the ways we talk about this, is by what happens to VO2, okay? What happens to the volume of oxygen that we're bringing in and using at the end of the electron transport chain. If you go from rest to walking quickly, to jogging slowly, to jogging quickly, to jogging very, very, very fast kind of things, there's this relatively kind of straight linear increase, okay? As work rate goes up, oxygen consumption or energy demand, energy use goes up. Very, very proportional. Okay? Now, the reason your watches work the way that they do, or your Oura ring, is that heart rate does the same thing. As VO2 goes up, heart rate tracks right there with it. And that's why we can use heart rate without ever having to measure VO2 to try to estimate the same sorts of things. Okay? Okay. Now, the part that I showed you guys, I'm resting, I start, it jumps right up, and then it levels off again. Where it levels off, okay, we call that steady state. Steady state. Up to a certain intensity or a certain work rate of exercise, aerobic metabolism increases and then it levels off and it will reach what we call steady state. Okay? We will talk about in the next few slides when that doesn't happen or what it means when that doesn't happen. That's what we're going to get. Okay? That's steady state. Start jogging, it takes it a little bit, but it comes up and then it stays right where I want it to be. It comes up, my heart rate stays there. That's called steady state. Okay? Now, and I'll illustrate this in a few slides, but I'll introduce it now. As intensity gets higher and higher and higher, okay, what energy systems are we going to have to begin to tap into more so as work rate gets higher and higher and higher? Maybe creatine phosphate, sure.
Glycolysis.
Glycolysis, okay, anaerobic metabolism. Right. I'm here, I'm standing, I start walking. Aerobic metabolism can provide pretty much all of it. As we get higher and higher and higher, one of the things that happens is aerobic metabolism probably is going to start to have to work really, really hard. It may not be able to provide all of our energy, so we begin to use more and more anaerobic. As that happens, especially once we get over lactate threshold, okay, we're going to see, if you graph aerobic metabolism during exercise, we see something called a slow component rise. And so it goes up and it tries to get to a steady state. Aerobic metabolism tries to get to steady state, but rather than getting there, what we see is this slow, inexorable sort of tick up or climb up in aerobic metabolic use at the same work rate. Okay? So when you're jogging very fast, when it feels difficult, it's much more difficult for us to get to a steady state on it. Okay, and I'll show you some more things about that, and we'll talk a little bit more about the why, but it's a really, really important kind of thing. Okay. Okay. So let me show you this graph. All right. And then we'll back up and we'll talk about something. I have oxygen consumption graph here on the left. Okay, that's this y-axis. This is on a bike, so it's watts or power output on the x-axis. Right? Very, very easy, progressively more difficult on the bike. What you see here, this is this linear increase in oxygen consumption with an increase in work rate. Okay? The other thing that it's showing down here, and this would be if we put you on a bike, and basically every second we make the bike power output get a little bit harder, So every time you pedal, it becomes progressively slightly more difficult. Okay, slightly more difficult, so that it's never going to get a chance to reach a steady state, and it just climbs like this. Then this dash line is showing blood levels of lactic acid or blood levels of lactate, right? Early on down here, we're not really having to see an increase. Boom, boom, boom. We're going to get to about here. It's going to start to deflect up. This is going to be lactate threshold. Right at about that, in a lot of people, you will note that the VO2, the slope of our increase in VO2 is going to shift ever so slightly. We'll talk about why that is in a minute. Big thing is oxygen consumption is relatively linear compared to work rate. And there's going to be this lag. At some point, we'll start bringing in more anaerobic metabolism. And that's going to that's gonna shift things ever so slightly. Okay? You guys with me so far? Right? Very straightforward, okay? Very, very sort of intuitive, okay? For exercise events that last longer than, let's just say 45 seconds, okay? Longer than 45 seconds. If we look at energy use over time, so think about this, back to our graph, okay, that I had you guys draw. In that transition phase where I go from rest to immediate shoot up in energy use, okay? During that immediate climb, right there at the very, very start, okay? Because aerobic metabolism is slow. Early on, as we shoot up work rate, we're going to use creatine phosphate, and we're going to use much more glycolysis in the first, let's just say, 30 to 60 seconds of that increase. Okay, it's going to go up, and then we're going to have energy use to level off. Early on, that first minute, lots of anaerobic metabolism. After that, it's going to begin, aerobic begins to catch up, and then after, let's just say, 2 to 3 minutes, depending upon the work rate, if we get to a steady state, it will be almost exclusively aerobic. Okay? For things that last more than, let's just say, 10 minutes or thereabouts, we're going to have a steady state. Usually we can get to steady state within 3 or 4 minutes in most people, if you're reasonably well trained, and then it just kind of stays that way. And there's data like people will put somebody on the treadmill, have them walk at the same speed for like 3 hours. VO2 goes up and it's just flat for like 3 hours, just a steady state that lasts forever and forever and forever. Okay? That's what's going on. So in that transition, anaerobic metabolism and then aerobic catches up. So here's that graph that I had you guys draw, okay? But what this graph shows is not overall energy use, it's just aerobic metabolic energy use. So imagine, here's 5 minutes of exercise on the x-axis. This is oxygen consumption or aerobic metabolism measured on the y. I go right from here, where everything is at 0. As soon as you start doing something, straight immediately up to whatever that energy demand is going to be. So on our first one, right here, where it's going to say, right at 50 watts, as soon as you start pedaling, it immediately goes up to here, okay? And then that is going to stay constant all the way across. So you guys can imagine, see how the line, the aerobic metabolic line sort of curves, it increases and it kind of curves slowly. And then after about a minute or so, it reaches where it's going to plateau off. It's going to have steady state. Okay. So this sort of triangle or this area up here at the start of exercise is going to have to be supplied by anaerobic calories. You guys will note as the work rate increases, it goes from 50 to 100 to 150, all the way up to say 300 watts, right? Then you will note how the VO2 curves slopes are initially relatively similar, but they're going to bend out and kind of get shifted to the right, which means it takes us longer and longer for them to reach steady state, which then creates a larger gap that has to be filled in by anaerobic metabolism. Okay? So lots of energy at the very, very onset of exercise, even if it's things like walking, is going to have to be supplied by creatine phosphate, kinase reaction, glycolysis. And then at some point, aerobic will catch up and we'll get our steady state and we'll be there and we'll be fine. So that part makes sense. I will tell you all what that is called in a few slides, but that's a very, very important sort of thing. Okay. Here in kind of the pinky purple, and Ella's favorite color here, and in the green, okay, you guys note how there's this little gap between the two lines, okay, and how especially at say 200 watts, how the top one, where you would think that it should level off, it kind of continues to slowly creep upward. that is illustrating what we would call the slow component rise in oxygen. At high enough work rates, especially if it's overlapping threshold, there's going to be a much, much more difficult time of actually getting to steady state. Okay, and so where you should see it level off, it's going to slowly begin to kind of creep upward. And that has some important implications for how long you can maintain exercise. Okay. So I'm here, I'm doing nothing. As soon as I start, just straight shoot up in need of energy, and then aerobic is going to sort of lag a little bit, and then eventually get to a steady state. So we're going to have to fill in the stuff from that lag with anaerobic. Okay. Okay. So this slide, this graph illustrates that exact concept. Okay. This is what I had you guys draw. The dashed line that you see here, where it goes straight up, it says start of exercise. The dashed line goes up, and then it stops and it goes directly sort of 90-degree angle to the right. What it's saying is the O2 requirement. What that really is that's the energy requirement for that particular bout of exercise. It is reps, and then as soon as I start, it immediately shoots up right to where we need it. Then the red line is measured aerobic metabolism, so measured oxygen consumption, and you will see that kind of exponential increase, and then eventually it will be able to supply all of the energy, and we get steady state. But the area that's kind of shaded in purple has to be provided by anaerobic metabolism. Collectively, that energy is called an oxygen deficit. Okay, oxygen deficit. Anybody taking economics? Anybody taking econ? Any business classes? Micro, macro, anything? No, you are like, ooh, yuck, Dr. Black. No. Okay. So we won't get into what a deficit is and what a debt is or anything else. Okay. Just imagine, anybody have a credit card? You guys ever put stuff on a credit card and you don't have enough money in your bank account to cover everything? You're like, you know what? Put it on the credit card. It'll be fine. Right? And so in some ways, what you're doing here in the purple is I need this now. It cannot be provided by aerobic metabolism, but we'll borrow some energy from anaerobic to make that up. That's this oxygen deficit. Okay. So there we go. Energy use at the onset of exercise that is not supplied by aerobic metabolism. We can try, if we get to a steady state, we can try to estimate what that area of O2 deficit is, and that's about the only way we can, other than putting you in an MRI machine, that we can try to estimate anaerobic metabolism or anaerobic metabolic contribution to exercise. Okay? Now, that's at the start. What about at the end? Okay? You stop exercising. Work rate falls from where it was, right, at the very top, immediately straight back down. Right? Certain amount, as soon as you stop, boom, it's right back down to the bottom. But aerobic metabolism will stay elevated for a little while. It does not immediately drop right off. It also sort of slowly, or kind of in an exponential way, kind of decay fashion, recovers back down towards resting state. Okay? This area here in kind of the greeny blue is called excess post-exercise oxygen consumption, or EPOC. Okay? EPOC. Anybody ever been to Orange Theory? Okay? Good. Orange Theory, as the things goes, is relatively scientific-ish in those ways. I know the woman who used to be one of their head of sort of physiology research things. She was also a Georgia grad. She has since moved on, but if you go to Orange Theory, they will tell you that if you accumulate a certain number of what they're going to call SLAT points which is based upon the amount of time that you spend in a certain heart rate zone, which is reasonably okay. Then you will, they call it afterburn, you will burn a certain amount of additional calories over the next couple of days over what you would have normally. What they are talking about is the physiological concept of EPOC. The higher the work rate, the longer the bout of exercise, the more energy you use during a bout of exercise, generally, the larger the EPOC. Okay? In many people, what we see after a bout of exercise is it's hard to measure, but this graph shows it coming all the way back down to rest. Okay? Anybody exercise this morning already? Don't act like they're exercising. One, okay? You mind sharing what you do?
I just ran a couple miles.
Ran a couple of miles. Great. You are still, even though you've been sitting here, you are still likely burning additional calories over what you would have at rest if you hadn't exercised. EPOC will stay elevated, especially if you do moderate to vigorous exercise, 24, sometimes up to 48 hours after a bout of exercise, because of these other physiological processes. What is happening during EPOC? You're resynthesizing creatine phosphate. You are removing lactate, shuttling it around. You are using extra energy to make sure that your sodium potassium pumps are running and you're repolarizing all your neurons and axons and sarcolemas. That you're using the calcium ATPase sufficiently and pulling all the calcium back into the sarcoplasmic reticulum. There's additional elevated rates of breathing that requires extra energy. Your core body temperature is elevated. It requires extra energy to help dissipate that heat and get us cooled back down to regular. Okay? All of that is what is going on here. Energy for basically everything that we do to return ourselves to homeostasis or to return ourselves to baseline after exercise stops is almost exclusively provided by aerobic metabolism. That's why it stays elevated for a little while after body exercise. That's what's happening. Jumping jacks, fucking old, not shape. So I've done this, and I'm like, right? You guys will be fine. And I'm doing that. I am in EPOC. And the longer it takes me for my breathing to come back down, the longer it takes me for my heart rate to come back down to baseline, the bigger the EPOC. Okay? Now we're going to do something that's going to seem counterintuitive. Okay? Energy from EPOC, for EPOC, comes only from aerobic metabolism. Okay? We take a marathon runner and a couch potato like me, and we both run a mile at the exact same sort of pace and intensity. Which one of us, at the end of exercise, is going to have smaller EPOC? Who's going to get back down to baseline faster? Very well trained person?
More trained.
More trained person. That's right. One of the things that EPOC can tell us is how well trained you are. Okay? And it's not necessarily the whole area, but it is this slope, or if you try to fit an exponential curve to all of this, you get these rate constants that go in there, right? Anybody want to do some fun math, talk about modeling exponential curves and rate constants and those things? No? Really? You sure? If you want to, come see me. We do this in the lab. It's terrible. But the slope of this will be steeper in a person that's better trained. Okay? So again, because the energy comes from aerobic metabolism, if you have a better aerobic metabolism, more mitochondria, more capillaries, better blood flow, you can recover back towards baseline faster. Okay? Another benefit of aerobic metabolism. In everybody, it's going to stay elevated and those kinds of things for a while, but generally the slope of all of this and how quickly it comes back is related to aerobic state of training. So even though I may not know how well trained you are, I can't measure your VO2 max, I can measure recovery afterwards and get to the same kind of thing. Okay. So related to oxygen deficit, okay, is sort of the slope or the rate of change in the red line. We call this aerobic metabolism or VO2, we call it onset kinetics. So kinetics is speed and rate and those kinds of things. And VO2 means aerobic metabolism. So all that this is really trying to get at is it's the same thing that we just talked about with epoch, but it's at the start. Okay. What's the slope of increase that's going on here at the very beginning of exercise? And the same thing happens. The better trained aerobically you are, the faster, the steeper the increase in oxygen consumption at the onset of exercise. And therefore, the smaller the O2 deficit. Okay? So these are some of the advantages of being well aerobically trained. Can anybody think of another way that I could speed up the onset kinetics, so that I could make the increase in this red line steeper and therefore make the purple O2 deficit smaller?
Other than training?
Other than training. What else could I have you do?
Doping?
Okay, sure. That's doing the same thing that training, right? In some ways, right? I give you some EPO, you got more red blood cells, like that, yeah. Then we're making aerobic metabolism better. What can I do without doing something like that? I can have every one of you do it right now. Oxygen-rich air. Okay, oxygen-rich air. That's an interesting, there is a little bit of an increase in O2 onset kinetics if you do that. Most of you guys know we're here, we're at sea level. Most of you guys, as long as you have normal hemoglobin levels, you're at about 98 or 99% hemoglobin saturation right now. The O2 rich air really helps us more kind of near max than it does at the start, but it would do a little bit. So it's a good idea. I have to coach my daughters. I'm coaching an under 6 soccer team this afternoon. Lord help us all. I don't know how I got talked into this. I mean, I know how I got talked into this, but today's our first practice. So we think 6-year-olds can kick a soccer ball in the right direction. Maybe we'll see. Do they know, like, don't pick the ball up? And our thing today is let's learn some names. Let's not like catch the ball with our hands. Let's kick it in the right direction. That's going to be the extent of practice. So we got to play this weekend. So anybody who wants to see something hilarious, 9 o'clock Saturday morning, which nobody will be doing. You're in the city, come to Cisterhill Park, and we'll probably be out there playing soccer, doing crazy things. I'm going to have the kids do this, one, because I got to kill the time. But there would be a real reason to do this. What do lots of people do before they go and exercise?
Warm up.
Stretch is usually part of getting up. Okay? If I will go from rest and walk a little bit, I've raised my energy use, right? Tie things back together, critical thinking. Why has my aerobic metabolism sped up? You guys remember? What was the last essay question on the test asking you about? I remember? Or like, no.
There was like there was over 40.
You had an assignment about it. If I want to make glycolysis go faster, I have failed. Utterly failed. Okay? Do we all agree that we can make glycolysis go fast?
Yes.
Do we all agree that we can make the Krebs cycle go faster?
Yes.
Yes, okay. What's the one thing that stimulates the rate limiting enzymes? In basically everything.
Oh,
ADV. So there's a rhyme and a reason to why we learn these things. I hope I can get that across. But if I want to make this go, if I walk before I run and I warm up, I stimulate PFK. I stimulate the Krebs cycle. I stimulate the electron transport chain. Okay? So now they're already going faster. So I was walking, but I've been walking quite a bit or jogging some. Then I stop. Now I got to go again. They're going to speed up. They're already kind of sped up, so that rate's going to be faster. Okay? This, much more so than stupid stretching, okay, is the virtue of warming up. It primes the metabolic pathways so that it will speed up your onset kinetics and reduce oxygen death. Okay? And we do that by making metabolism run beforehand. Don't just go like I'm walking, gotta walk some, you gotta jog some, you kind of gotta get warmed up in that. Okay? All right. Talked about those things. So I'm just kind of going through this, guys. We talked about the factors. Y'all said mentioned this on the thing that I just do this sometimes, so I'm sorry. Factors responsible for EPOC. We mentioned many of these. Okay, all of this stuff is going on as we are recovering, sort of down through bringing VO2, bringing oxygen or energy use back down towards baseline levels. All of those things are going on. This is the same concept. It's just shown sort of in a map like all of this. It's the same thing. It's resynthesis of creatine phosphate, converting lactate to glucose, restoring muscle and oxygen blood supplies. Text on this one, this is just sort of a concept map that's here. Okay. In this slide, I want to illustrate, again, a thing that's happening during EPOC, which you've got sort of O2 deficit, oxygen use, you can see here, right? You can see EPOC here on the right, but then overlaid in blue on this is creatine phosphate levels. So this is creatine phosphate. To measure this, we have to put you in an MRI, okay? We do something called magnetic resonance spectroscopy. Very cool, very accurate, but you know, it's $2,000 an hour to put you in a magnet. I'm sorry, how much? Yeah, it's about two grand. Anybody has, I don't know, like $5 million like laying around? What you want to do is you want to buy a magnet and open a radiology center, because insurance reimbursement is it's about $2,000 an hour for use of a magnet. Okay, yeah, it's crazy. So it's nuts. When I was in grad school, they built one and installed one on campus at UGA. In the morning, they leased or they sold the time out to the vet school. We got to see LSU's mascot, Mike the Tiger, came and got an MRI at UGA, which I thought was wild. That they didn't have one at LSU, and those kinds of things. You see dogs and cats and all these things getting imaging and stuff done, really cool. And in the afternoons, we would get to use it for research. And so we could do things like this if you wanted to do spectroscopy, but here we're resting high PCR at the start of exercise. When you use anaerobic metabolism, PCR levels fall, you're using creatine phosphate, then it kind of levels off down here, right? It kind of does the exact mirror image or opposite of this. And as soon as you stop, then you begin to resynthesize PCR. And so we're using the extra ATP being made from aerobic metabolism to put the phosphate back onto creatine and restore our creatine levels. Okay, so that's just illustrating one of the things that's going on during all of this. Okay, so kind of a very cool concept. So it's the same idea that the faster or the steeper the slope of creatine phosphate recovery, corresponds to a steeper slope of decline of oxygen use, both of which indicate better mitochondrial function. Faster recoveries of these two things indicates better aerobic state of training, all of this. You can do a similar thing in my lab or in Dr. Larson's lab or in Dr. Kellerman's lab using measures of oxygen saturation on red blood cells. You kind of see the same thing. You start exercising and O2 saturation falls and then you stop and it comes back basically. And we can use that as a way to kind of to map out the same sort of thing. Okay. Okay. The next several slides all show the same thing. Okay. You don't have to know them. You don't have to recreate them. But I wanted to give you guys some visuals to try to illustrate. Okay. Looking at the size and magnitude of O2 deficit in green, and then epoch in yellow, and then you can kind of see the slope of this red line, which is going to show us kind of the rate of recovery-ish. They should have just fit it to the curve, right? And that's fine. Here, this is light aerobic exercise. So this is what it would look like at the start and the stop of walking, okay? Now let's do moderate to heavy aerobic exercise, okay? You will note that everything gets taller, so our energy demand is up. The green area gets bigger. We need more anaerobic metabolism at the start. And then the yellow is also epoch is much, much bigger. Okay? Epoch is also much bigger. Don't worry about the red line versus the orange line. That's talking about the fast and slow component of the epoch curves. That's a mathematical thing we don't need to worry about. I really want you to just pay attention to the size of the green and the size of the yellow. Okay. There's Orange theory in a nutshell, right? If you accumulate, you do walking, it looks like this, and it stays elevated for a little while. If you do enough high intensity stuff or higher intensity, it's bigger, and then it takes it longer to come back down. That's extra calories, which equals more Doritos, or whatever it is that you like to eat. It's your favorite thing. Okay? That's the point there. And then here's the weird thing. This one is all out maximal exercise. So this is exercising at a place where, right, you're going to essentially reach your VO2 max. You will note that basically we have this sort of above VO2 use, above aerobic metabolism. We're using even more anaerobic metabolism, and our recovery is going to get even bigger. Okay. So that is mostly what's going on there. Okay. As we near the end today, we can learn a few other things about what's happening aerobically in our aerobic metabolic systems by measuring or monitoring, right, carbon dioxide production versus oxygen use. Okay. So I'm going to show you guys an equation to calculate something that we call the respiratory exchange ratio, or RER. This is a whole body in a person version of something that originated in isolated muscles or in animals that was called the respiratory quotient. Quotient just denotes, right, division and those things. So the equation is the same. But when we measure it in people, we call it RER. Okay. And we calculate this by taking the ratio. So you take the volume of expired carbon dioxide, and you divide that by the volume of consumed oxygen. So it's VCO2 divided by VO2. Okay. So what this tells us, right, is the relative contribution of fat and carbohydrate as an energy substrate during aerobic metabolism. Okay. Because fat is larger and it has more carbons, it has to go through the Krebs cycle more. Okay. It goes through the Krebs cycle more to be broken down. it will make more carbon dioxide. So when you use more fat, for any amount of oxygen that is consumed or used at the end of the electron transport chain, there's extra CO2. So what that means then is if numerator gets bigger and the denominator stays the same, then our ratio falls. Okay. So fat burns more oxygen than carbs, it makes more CO2. That's what's going to happen. So RER, we get these ranges of values, and they range from 0.7, and it should be to 1. Some weird things happen at high intensity exercise where it gets a little more. Okay. When we use exclusively fat, all I did was make you eat Crisco. Eat only fat, like a day. I would drive your RER all the way down to about 7. Conversely, if all I gave you to eat is, I don't know, Skittles, right? Just here, have some glucose. All you're getting is glucose for like a day. Then I would raise your RER up to 1.0. So 0.7 denotes only fat being burned. 1.0 denotes only carbohydrates. Most of the time at rest, you guys are about, instead of about 0.8 to about 0.82. So you burn a little bit more fat at rest than you do carbohydrates. As exercise intensity increases, remember, fat is broken down more slower, so we use more and more carbs as exercise. So as you increase your work rate, RER creeps up towards 1.0. Then a weird thing happens. I make extra CO2, and the ratio can get up over 1. So once you make lactic acid, have something in your blood called bicarbonate. I had to eat some bicarbonate this weekend. My stomach was upset. I had some Tums. Tums has sodium bicarbonate in it. It's a base, right? And so you store carbon dioxide in your blood as bicarbonate. So when you make lactic acid and the pH changes, it buffers the pH change. It soaks up those hydrogens, but what it does as a response to that, though, is it releases carbon dioxide in your blood. So you now have extra CO2 that you can breathe off that has not come from the Krebs cycle. Okay? That lets us get our RER up over 1. Okay. This will be one of our measures and one of our criteria that you get a good VO2 max test. That your RER is usually over 1.1. All that really tells us is that you tried hard. You're well over your lactate threshold when you do that. Okay? That's what RER is. It tells us fat versus carbs. You can come to my lab and sit down. We can do this to you for free. Or you can, I didn't look up how much it costs this morning, but you can Google, they make things, these little kits that they'll send you, you breathe into a thing and then it tells you like immediately like what it thinks that you're burning, fats versus carbs at that exact moment. They probably charge you 50, 80, $100 a shot to do that. All it's doing is this. All it's doing is this little snapshot of what your RER is. Breathe into this thing. Okay. And it basically doesn't tell you anything of use. That thing doesn't tell you anything of use because it's just what are you getting from like 2 breaths? What did you eat for breakfast or not? And that kind of thing. Okay. The next slide shows you how these calculations are going to work. You don't have to know this. Okay. But I wanted to illustrate for those of you that are like me and you want to see the work that goes into this from a mathematical standpoint. RER, or what we call R, is CO2 divided by VO2. Here is how we would arrive at the breakdown of 1 molecule of palmitic acid. So you have its organic compound here, right? C16, H32, O2, with 23 oxygen molecules makes 16 CO2s and 16 waters. So you then take those 2 things and you divide them and you get 0.7. And then here's the equation for a similar amount of glucose, so because, right, it's different, C6H12O6 as opposed to this, then the ratio looks a little bit different. Okay, that's how we arrive at those things. This next table is going to show us what I verbally told you guys. Here's your R or your RER value from 0.7 all the way down to 1.0. And it tells us then how much of the energy you are getting at that moment from fat versus carbohydrate. Okay, fat versus carbohydrate. This is very, very sensitive to what you just recently did. If I feed you fat, I make your RER. If I feed you carbs, I make your RER go up. And it's very sensitive within, you know, I don't know, an hour or something of doing all of that. And then it kind of flips back around. You're just going to use whatever you're feeding the aerobic metabolic system. Okay? Okay. So I'm going to do this side of things. This next slide first. No. We'll stop here. Okay? We'll finish this part off on Wednesday. I'll give back tests on Wednesday. We'll try to figure out. All right. Okay. Thanks, guys. We'll see you Wednesday. Yeah.